Hello guys, hope you're doing well. Welcome to the new chapter of control. So today I'm so excited because that we are going to talk about some kind of, you might probably heard about that in my previous some kind of, but at this point I would like to focus more here, and we would like to actually step down a little bit more inside the closed loop controller, and we would like to see that what would happen if we change the gain. Because so far when we are talking about everything related to our controllers, it was a transfer function, it was the Laplace equation, and after that we talked about the poles and zeros, but we didn't actually touch the fact that what would happen to gain, or maybe decreases, because as you guys know, gain is going to play an important role in the controller system, and it's going to tell us that how your system is going to be stable, margin is stable, or unstable. Without further ado, let's talk about it. So as I just mentioned, this video is going to be long, so probably I'm going to divide it into different chapters. So let me just start it with a chart. Let me just start with a diagram that actually what we are going to talk about. So as you guys know, on the previous chapter, we talked about the system representation. Again, we know that in some kind of normal mode, we cannot just build the physical system by itself. First of all, we have to do the studies, we have to do the simulation, then we have to make sure everything is okay, and also by considering the fact that we do have some tolerances in our actual system, then try to build that. Because as you guys know, there are lots of examples that people built something, and after that they found that the system doesn't work because they didn't pay attention while they were doing the calculation and simulation. So the very first thing that we learned was about the system representation. As we all know, we had the transfer function and mathematical transition. So why we use the transfer function? Again, it was easy because it can show the relation and output. But we talked about it and we say that, okay, because the time domain form is a little bit of complicated, especially when you have different kind of systems side by side, maybe in series or in parallel, we would like to talk about the Laplace. It will be easier, and at the end of the day, the only thing you have to convert it back to the time domain and everything would be fine. Then we talked about stability analysis, because as you guys know, when you're talking about some kind of a transfer function, you do have a fraction, and in this fraction you have the zeros on the numerator and you have the zeros on the denominator. Zeros. So by finding the poles and zeros, we can understand that our system is going to be stable, unstable, or marginally stable. Then we talked about the feedback control, which is going to be very important. We would like to try to put our focus mostly on the closed loop controller. Yes, we do have the open loop controller, it's okay, but as you guys know, while the open loop controller is going to be simple and it was some kind of like expensive, it doesn't have that much of the some kind of preciseness that we need, and at the end of the day we are closed. But at all of these cases, we try to focus more on the transfer function itself. We didn't talk that much about one specific element, on one important element that we call it as gain, because as you guys know, gain is going to act as a valve and it's going to be connected to your whole system. By increasing or decreasing that, you're actually just changing the position of your poles and zeros. Don't careful about that, you could cause some catastrophic issues. That's why we do have the concept that we call it as a root locus. So what is this concept? This concept related to your system and what would happen in your S-plane, because we know we are talking about the S-plane, it has the x-axis and y-axis, and we would like to model our poles and zeros there in order to understand that what would happen to the system in the future. So by increasing the gain, we actually would like to know that what would happen to the system. So we do have some kind of a system that we call it as root locus. It's going to help us by using different kind of techniques, and after that we can see what would happen in the future. So without further ado, let's talk about it. But just before talking about the root locus, I really would like to have some step backs and see that, first of all, what was the transfer function. Just you can see some of these kind of sequential chapter as the review itself, and then we would like to solve a couple of equations, couple of examples, and at the end of the day, when we are making sure that our some kind of knowledge is solid, we can move forward to the root locus and see what would happen if we increase or decrease the gain. So as you guys know, the transfer function is a function that shows the relationship between your input and output. So imagine that you do have a system like this, that you do have your a2 times y to the power 2 of prime, a1 times 1 y prime plus a0 y equals to b1 u prime plus b0 u itself. So u is the input and y is the output. So since this model right now is going to be an algebra, a mathematical, equation. As you guys know, we don't like the mathematical equation not that much in this form, or it's a time domain. That's why we are using the Laplace transformation. The Laplace transform is going to move or shift everything from the time domain to the frequency domain, and then it's going to help us to find the relationship. So if you do that, if you some kind of do the calc, so as you can see over here, I do have a2y prime. So if I move it to the Laplace transformation, it would be a2 s2y big Y, and about this guy a1 sy. About this guy is just a0y. Then we do have the same scenario about the input itself. So at this point, we don't know what is happening to the input. Most of the time, we just consider it as the unit function, but right now we don't. So it would be b1s, and finally it would be b0u itself. As you can see over here, it should be some kind of capital, not the normal. So when we do have over here, the only thing you have to do is just using the factoring technique. It means that just consider the y and all of the coefficients alongside with the fact of u on all of the coefficients. Then you can find this fraction. This fraction shows the relationship between input and output, and at the end of the day, you do have something like this. So this is the guy that we are going to talk about it, or we've been talking about it so much, because this guy is going to give you the casual zeros and poles, and based on that, you can understand what is going on in the system. So let's have some kind of try to review the previous concept. The very first one was about the order. So when we were talking about the order, most of the time we are referring, not most of the time, all the time we are referring to our some kind of denominator part of the fraction itself. So order means that higher power of s in the denominator itself. So casuality means that if we would like to consider the fact that our transfer function is stable, or at least is going to reach to steady state conditions, we have to follow rule of thumb. A rule of thumb would say that the numerator degree, it means that the biggest power of s over here should be smaller than or equal to the denominator degree. And finally, we are talking about the linearity. It means that system must be linear time invariant. We talked about it before, and also we are going to some kind of mention it time to time. So it's good to know that. And then I put another some kind of example for you. I believe you can do it better than me. It's exactly like the same, exactly like the formula itself. The only thing that I gave you is that instead of just b1, b0, a2, a1, and a0, I gave you numbers. So you can put it there, and after that you can find your transfer function easily. So we had the rules of thumb, and the rules of thumb would say that when we do have the Laplace transformation, and we are going to resemble our some kind of fraction itself in a complex plane. We know that the complex plane is going to be a plane that has the real values and has the imaginary values. So if our poles and zeros are going to be on the left side of this plane, we say that our system is stable. If there's going to be on some kind of y-axis, we say that we do have the marginal stable, and if everything or at least some of them would be on the right side, we say that we do have the unstable system. So this is the definition of the Laplace. So Laplace of the time domain is going to be integral of 0 to infinite of ft times e to the power negative st dt. So by converting our mathematical or the time domain, actually we are trying to decrease the complexity of our some kind of the modeling of the system itself. So since we are talking about the Laplace transformation, you already know about that, but we do have some kind of basic Laplace transformation. First of all, we do have the pulse. First of all, we do have the pulse itself. So the Laplace of pulse is going to be just 1. The ut, or some kind of the unit function, is going to be 1 over s. T to the power n times ut is going to be n factorial divided by s to the power n plus 1. E to the power alpha t times ut is going to be 1 divided by s minus a, and you can see the relationship for the sine and the cosine. So most of the time we are working with this 4, and we do have the sine and cosine, but we would better to put your focus on the first 4 itself. And also I put an example over here for you. Again, it's so simple. The only thing that you have is just convert this guy to the Laplace transformation based on the thing that I already told you. So again, if you have any issue, please comment me down below. Then we do have another thing, the wiring system. It means that we do have the signal flows, and we would like to talk about the closed loop. So as you guys know, the closed loop means that not only we have to move towards the output from input to output, we also do have the feedback, and the feedback comes from the output, and it's going to some kind of the error detector. It means that the difference between the input or your desired value and the value that you already have, because this is the job of the feedback controller, is going to give us the error, and by some kind of putting this error inside our controller itself, the open loop gain or open loop controller itself, we can control our output. So for the closed loop controller, we do have the formula. It's going to be gs divided by 1 plus, imagine that if you have some kind of at this point we would just consider that h of s, or the feedback gain, is going to be 1 1. So if you can see over here for the closed loop system itself, the denominator is going to be 1 plus g of s is equals to 0. So what does that mean? It means that by keeping this guy equals to 0, I can find the roots. By finding the roots, I can find the poles. By finding the poles, I can compare it in some kind of in my system itself to see that it's going to be on the left side or the right side. Then I can decide that my system is going to be stable or not. Again, as you can see over here, I put another example for you. Again, if you have any issue with any of this example that I put for your more practice, just itself. So the actors over here are going to be poles, zeros, and it means that the physical meaning to that. Because as you guys know, we say that, okay, if we do have the poles, and these poles, by the way, are going to be the roots of the denominator, it means that those guys a path or show me a way. It means that they are going to determine the natural modes of the system itself. So a pole at s is equals negative alpha or negative a. It means that it's going to be on the left side of my s-plane, can be shown as e to the power negative alpha t. So it means that at the end of the day, I do have the system that would start from here, but when it just time pass, because e to the power negative alpha t is an exponential function, is going to be smaller, and my system is going to be stable. On another hand, we do have the zeros. While zeros, they don't have that much of an effect over some kind of steady state response or the long-term response. They do have some kind of effect over this. It means that the values of that makes the numerator 0. Again, we are referring to our what? We are referring to our some kind of closed loop transfer function itself. So by this way, it means that the zeros are going to shape the magnitude, phase, and the speed of the response, and can mathematically cancel the poles, which we are going to talk about a lot in the future, especially when we are talking about the compensation of the system itself. Then we had some kind of thing. Then we have the behavioral profiles. It means that the first order or going to be the second order system. What does that mean? The first order system are just going to be simple decay. It means that your transfer function is going to be like this. And why? Because it's the first order, because the s or the power of s is going to be 1. And we can see that, for instance, we were talking about the normal capacitor. By considering the fact that my pole is going to be on the left side and I don't have any 0 on the top, I can say that my system is going to act like this, or I can say that my system is going to be e to the power negative omega n t, which means that at the end of the day, my system is going to be stable based on the omega n itself. On the other hand, we do have the second order. It means that at this point, my denominator is going to be a little bit more complex. And by finding the zeros of this guy, I can understand what would happen to the system itself. Imagine my zeros is going to be like this. So at the end of the day, I know my system for sure is going to be stable. Obviously, it do have some kind of features, like it has overshoot. The race time is going to have the steady state error, and out of the end of the day is going to be what is going to be steady state. So imagine we do have the second order system, and the omega n is going to be 5, and some kind of the zeta is going to damping 6. So we have to calculate the exact location of the poles. By using this formula and putting just numbers and make it as 0, you can find the poles, and at the end of the day, you can make sure either your system is going to be stable or not. So this is another some kind of review related to all of the features that you have for your system itself. So imagine that I do have this stable system. In the meantime, I would like to calculate a couple of things. The very first thing that I have to find is about the delay time. So what does it mean? The delay time is the amount of time that it takes for my system in order to respond to the changes itself. So this is not the value that we use it most of the time, but at least good to know. Then we do have the rise time. The rise time means that how much time does it take for my system to reach from the 10% of its maximum to 90% of its maximum itself, if we assume that this part or this line is going to be my maximum. So this is something that we call rise time or TR. Then we do have the peak time. How much time does it take from the beginning to the fact or to the place that my system is going to reach to its maximum level? By the way, at this point, this is not the maximum. The maximum level is the time or is the part that my system can reach it to. Overshoot is another concept. Overshoot is the difference between the maximum value and the steady state value. So this is something that we call that overshoot. And we do have another thing as the settling time. So what is the settling time? The settling time means the amount of time that it takes for my system to reach to a point that the difference between the actual value, imagine that this wave is the actual value, and the values that we desired, which is going to be this line, is going to be between 2% to 5%. It means that the error, which as we all know, the error is going to be the difference between the actual value and subtracted by the some kind of desired value, desired variable, you can put it into some kind of the absolute value, because at this point we don't care about the positive and negative, we just care about the error itself. So if you reach the fact that your error is going to be 2 to 5%, it means that the comparison of this difference and the final value that you need, it means that you're at the settling time, or it means that you are reaching to the time that you can say that it's settled. So at this point, you have to consider the trade-off. Obviously, you cannot minimize the overshoot and settling time simultaneously without fundamentally moving the poles itself. So while you're trying to design a system, obviously you cannot have everything that you need at the same time. At some point, you need to have sacrifices, but you also have to look at your system to see that at what point is going to be the best for yours. At this point, I'll put some kind of examples over here. You already have an answer and you can just some kind of read it out. So when we are talking about the system, or when we are talking about the system stability, most of the time we are referring to the place of the poles. In the future, you would see that just knowing the place of the poles is not going to be enough. And also we talked about in the previous part that it is also important for our system to be controllable, or also to be observable. So at this point, let's try to make it simple. Imagine that you do have the system and its poles are going to be on the left side, all of them. So we can consider the system is going to be what is going to be stable. Why? Because all poles strictly are in the left half plane, or we call it as LHP. Imagine that you do have the system that it's some kind of poles are not going to be on the left side or right side. Oh, sorry. The poles are going to be all of them on y-axis or imaginary part. So we call the system as a marginally stable. It means that the system is not going to reach the unstable condition, but not also in a very good position of considering it stable. It is going to act constant all the time. And finally, we do have the unstable system. So as you can see over here in our unstable system, everything is going to be collapsed, because what I do have a pole on the right side and the system is going to be out of control itself. Imagine that I do have a system that its characterization is some kind of a denominator part is s plus 1, s minus 2, and s plus 3. While s plus 1 and s plus 3 are okay, s minus 2 is going to make us a problem. So we know for sure my system is not stable itself. So why instability is so important? Why we do have to care about that? Because as I just told you, there are numerous number of examples that you can see that if we don't care about our system instability, while it could be so small, for instance, at this point, you can see that the only issue that I have is going to be 0.01. While at the beginning of the point, this part or this portion is not that bad, after some time, this portion increases. Because remember, when you're talking about the transfer function, we are not talking about the fraction. Actually, we are talking about the exponential function. An exponential function, even with this small amount of power, can increase so fast. So at this point, I gave you a couple of examples that what happened in actual life. The very first one was about the Chernobyl reactor. And actually, at this point, we had the positive reactivity feedback. As we guys know, most of the time, or all the time, we need our feedback to be negative, because the feedback itself should be subtracted from the input. But if we do have the positive feedback, our system is going to get confused. And by getting confusion, exponential power growth phenomenal. And after some points, everything is going to collapse because injected more and more. Another one, we do have the Tacoma Narrows. It means that we had we had a bridge, and inside that bridge, we had everything some kind of solid. But at some points, the engineers didn't consider the fact that the wind itself would have some energy, and the wind energy, or the frequency of the wind that was blowing, was the same as the natural frequency of the bridge while it was swinging itself. So when we do have the wind, and when it was some kind of pushing or hitting the bridge at the exact time or at the good time of the natural frequency, it means that your swinging is going to get worse and worse and worse, and at the end of the day, your system is going to collapse. And also, we do have some kind of, in the pilot section, imagine that we do have the flyby, some kind of wire software, and we do have an error, and again, like the power feedback is not good, or we do have unstable system, and everything again is going to be collapsed, and means that your plane doesn't have that much of a handle, and your pilot doesn't have some kind of choice rather than just ejecting from the system itself. So it is very important. Again, at this point, I'll try to talk about some kind of the system itself. And when we do have the roots on the left side, it means that you have to find the factor of 1 plus gs times h. If you guys can look at this one, why we do care about that? Because h of s was a feedback gain, and as we all know, the feedback gain was 1 most of the time. But at some points, when your feedback gain is going to have something in it, we should consider the h of s and multiply by g of s and plus 1. So this guy guy is going to be a root of your transfer function. And whatever that you have inside of this guy, or whatever outcome that you get, is going to be the place of the poles. So you can see all poles are going to be on the left side. So it means that your system is going to, what is going to be stable at the end of the day, even if you have the disturbance, is going to be what is going to be vanish. On another hand, when you have the system where everything is going to be on y-axis, you do have the condition right there, it's marginally stable, and at the end of the day, you do have honest. So why we do care about that? Why we do care about all of these information from the beginning till now? Because as I just talked about it, there is one important element in most of their function that we call it as gain. So most of the time we consider the gain as 1, so it didn't cause, or at least not that kind of important issue for us. But imagine that you do have the system and its gain, it's not feasible, and its gain so high that your poles, or the location of your poles, is going to be different. On that time we actually care, because we have to see what would happen to our gain. So obviously we cannot put some numbers inside this formula itself and try to solve it every time, because obviously we are going to lose a couple of things. That's why we do have the root locus. Root locus would tell us that what would happen to k, or decrease the gain, what would happen to your whole system, or what would happen to the location of all.